Hi, in this video, we will discuss the noncovalent intermolecular forces in liquids and solids. Liquids and solids can be considered as condensed states of matter because, for example, we know that liquid water can be condensed from water vapor. Liquids and solids are different from gases because at ordinary temperatures and pressures, for example, at room temperature and standard atmospheric pressure, the particles in a liquid or solid are closer together. Now, because of this, the physical properties of a liquid or solid are influenced by what we call noncovalent intermolecular forces, which are simply the strong interactions between the particles of a liquid or solid. Before we present the three types of noncovalent intermolecular forces, let's differentiate the nonpolar and polar particles. First, if the difference in electronegativities of the atoms in a bond, is less than 0.5, then the bond is nonpolar. By the way, recall that electronegativity is the tendency to attract electrons. Okay, so for example, let's say we have a bond between carbon and hydrogen. Okay, so if we compare their electronegativities, for carbon we have 2.5 and for hydrogen we have 2.1. So the difference between the two electronegativities is 0.4, so that is less than 0.5. Therefore, the CH bond is nonpolar. Okay? Otherwise, if the difference in electronegativities is at least 0.5, so that is 0.5 and above, the bond is nonpolar, rather polar. For example, let's say we have a bond between hydrogen and oxygen. For hydrogen again, okay, from the previous example, we have 2.1 for the electronegativity. For oxygen, the electronegativity is 3.5. So if we get the difference, that would give us 2.5, okay, 1.4. So that is greater than 0.5. Therefore, the hydrogen-oxygen bond is polar. Okay, so this means that since oxygen has more or has higher electronegativity or has higher tendency to accept electrons, then we can say that this end, where we have the oxygen is partially negative, and the end where we have the hydrogen is partially positive. Okay, so they have those partial charges. Okay, next, another factor that we have to consider in determining whether a particle is polar or nonpolar is the shape of the particle and distribution of electrons around the atoms consisting the particles. So if that shape is symmetrical, then the particle is nonpolar. For example, let's say we have carbon dioxide. So the shape of carbon dioxide is like this one. So you have oxygen positioned directly opposite each other. If we consider each bond, no, so between oxygen and carbon, so for oxygen, again, let's compare the electronegativities. For oxygen, we have 3.5. For carbon, we have 2.5. And the difference of that is, of course, 1. Now, that is greater than 0.5, right? Therefore, each of these two bonds is actually polar. Okay, but again, since those two bonds are directly opposite each other, okay, so the shape of the particle is symmetrical. Therefore, the two polar bonds will cancel out, okay, such that, okay, the carbon dioxide is not a nonpolar particle. Now, Otherwise, if the shape of the particle and the distribution of electrons, okay, around the atoms are not symmetrical, okay, then the particle is more likely polar. For example, let's consider water. The shape of water is as follows. So you have oxygen, let's say above, okay, then below that, okay, are the two hydrogen atoms. So again, okay, from this example, okay, the hydrogen-oxygen bond is a polar bond. Okay, so polar, polar. But since they are not, okay, directly opposite each other, they will not cancel out. Okay, such that oxygen, which is above the hydrogen atoms, okay, oxygen again, no, has higher tendency to accept electron because it has higher electronegativity. Therefore, this the yeah, this end of the of water is partially negative. Okay, and each hydrogen atom has a partial charge of positive. The first type of non-covalent intermolecular forces is the London force. This is developed when a temporary dipole in one molecule induces temporary dipoles in adjacent molecules. For example, we have this first molecule. Let's say for some reason, the distribution of electrons in this molecule is changed, such that we have more electrons on the left end, and because of that, the left end will have a partial negative charge, and the right end will have a partial positive charge. Now, this temporary dipole will induce another temporary dipole in an adjacent molecule. For example, we have the second molecule. Since this right end of the first molecule is partially positive, it will tend to attract the electrons in the second molecule, such that the left end of the second molecule will now have a partial negative charge, and the right end will have a partial positive charge. Now, if we have a third molecule, let's say that is adjacent to the second molecule, this right end of the second molecule would again attract the electrons of the third molecule, such that the left end of the third molecule will have partially negative charge, and the right end will have partially positive charge. And the induction will go on as long as there are adjacent molecules. The London force is present between molecules of all molecular substances. So remember, for all molecular substances, or for all molecules, we have London forces. For example, in water and in carbon dioxide. So these two are molecular substances. The London force is also present between atoms of noble gases. For example, helium and xenon. So we know that noble gases hardly react with other elements, or even with another atom of the same element. Okay, so for example, we have a helium gas. So let's say you have this helium atom and then this another helium atom. So each atom is neutral. Okay, so for these two to be able to attract each other, temporary dipoles should be produced. Okay, through induction. Now, London forces, remember, or London force is the only non-covalent intermolecular force present in nonpolar molecules. So if we are given nonpolar molecules, okay, we are sure that only that we have only London forces. Okay, for the non-covalent intermolecular forces. For example, in carbon dioxide, so that's nonpolar. Another nonpolar molecule is carbon tetrachloride. Now, the magnitude of London forces ranges from 0.05 to 40 kilojoules per mole. Okay. Yes, remember that London forces. Okay, London forces are due to the uneven distribution of electrons within a molecule. Okay, therefore, the magnitude of London forces is directly proportional to the number of electrons in a particle. So, the more electrons a particle or molecule has, the stronger the London forces. The second type of non-covalent intermolecular forces is the dipole-dipole force. This is due to the attraction between oppositely charged ends of permanent dipoles. So we need permanent dipoles, not temporary dipoles, but permanent dipoles. Therefore, the dipole-dipole force is present only between polar molecules. For example, we have water, ammonia, and ionic compounds. So, given polar molecules, we should know that the non-covalent intermolecular forces are dipole-dipole force and London forces. Because remember in the previous slide, we said that London forces or London force is present in all molecules or molecular substances. So, for example, we have hydrochloric acid or hydrogen chloride. First, let's determine whether this bond is polar or nonpolar. So, let's compare the electronegativities. For hydrogen again, that's 2.1. For chlorine, that is 3. The difference between these two values is 0.9. That is greater than 0.5. Therefore, the hydrochloric, this bond or the entire molecule is polar. Therefore, we have here a permanent dipole. Okay, where because chlorine has higher electronegativity of 3, the end with the chlorine is partially negative, and the end with hydrogen is partially positive. So this right end will attract the end of another molecule with hydrogen, right? Because that is partially positive. If we have here another adjacent molecule, this right end of the second molecule will attract, okay, the end with hydrogen. Because again, that is the end that is partially positive. The magnitude of dipole-dipole force ranges from 5 to 25 kilojoules per mole. Now that is, well, at least the lower end is greater than the 0.05 for the London forces. Remember, for the London forces, the range, the magnitude ranges from 0.05 to 40. So that means that in most cases, the dipole-dipole force is stronger than the London force. Okay, so yes, remember that again, dipole-dipole force is due to the permanent dipoles. Therefore, the magnitude of dipole-dipole force is larger when the molecules are more polar. In other words, the more polar a molecule or particle is, the stronger the dipole-dipole force. The third type of non-covalent intermolecular forces is the hydrogen bond. This is the attractive force exerted by the hydrogen atom in the XH bond. So we have a hydrogen atom bonded to an atom X. Okay, and the attractive force is exerted on the lone electron pair in another atom Z, where the atoms X and Z can be fluorine, oxygen, or nitrogen. So we can remember here the acronym FON, which is again fluorine, oxygen, or nitrogen. For hydrogen bonding, again, we need a hydrogen atom that has a covalent bond, okay, with an atom X, which can be fluorine, oxygen, or nitrogen. And we need another atom Z, which also can be fluorine, oxygen, or nitrogen. And yeah, that atom is or has a covalent bond with another atom. So in hydrogen bond, this hydrogen atom is attracted to a lone electron pair in in Z. So we need at least one lone electron pair in the atom Z. Okay, for example, let's say we have an arbitrary number of carbon and hydrogen. So let's say CmHn, and let's say that is bonded to an oxygen, then we have a hydrogen. So in this case, most likely this oxygen will have two lone electron pairs. That is to gain 8 electrons in the outermost shell. Okay, so in this case, okay, how many hydrogen bonds can we have? First, well, we have here hydrogen. Okay, bonded with this oxygen. Okay, so this hydrogen will be attracted to the oxygen of another atom. So say we have here CmHn. Okay, again, so you have here oxygen and hydrogen. So this hydrogen will be attracted to one of the lone electron pairs in oxygen in another atom, or rather molecule. Okay, then these two lone electron pairs will also be attracted to a hydrogen atom. A hydrogen atom of another molecule. So say we have here CmHn, then you have O, and then H. Okay, again, so this H will be attracted to this lone electron pair. The same is true, okay, of the other lone electron pair of this oxygen. So let's say we have here CmHn, then we have O, okay, and bonded to that is the H, which will be attracted to this lone electron pair. So in this case, we have 1, 2, 3. In summary, we should remember the following. For all nonpolar molecules, the only noncovalent intermolecular forces present is the London force. Given a polar molecule, the noncovalent intermolecular forces present are the London forces and the dipole-dipole force. And given a polar molecule with a hydrogen atom bonded to fluorine, oxygen, or nitrogen, the noncovalent intermolecular forces present are the London forces, dipole-dipole force because it is polar, and the hydrogen because of the hydrogen atom bonded to fluorine, oxygen, or nitrogen. Since the particles of a liquid or solid are closer together, its physical properties are influenced by the strength of the noncovalent intermolecular forces present. For example, strong noncovalent intermolecular forces cause or result in higher boiling point and higher melting point. So since strong noncovalent intermolecular forces are hold the particles together, we have to heat the liquid or solid to higher temperature in order to boil or melt the substance. In these exercises, we have to identify the noncovalent intermolecular forces present in each substance, and based on that, we have to predict which substance has the highest boiling point. In other words, which substance has the strongest non-covalent intermolecular forces. But before we try the items, I think I forgot to mention that the magnitude of hydrogen bond ranges from 10 to 40 kilojoules per mole. Now that means that among the three non-covalent intermolecular forces, the hydrogen bond is the strongest. So let's consider chlorine gas, that's Cl2. We have a chlorine atom bonded to another chlorine atom. So the two chlorine atoms are directly opposite each other. Therefore, the shape of the molecule is symmetrical, and so is the distribution of electrons around the atoms. Therefore, the chlorine gas is a nonpolar molecule. And we know that the only non-covalent intermolecular force present in nonpolar molecules is the London force. Now let's consider hydrofluoric acid. So we have hydrogen bonded to a fluorine atom. First, let's consider or let's determine whether this bond is polar or nonpolar. So let's compare electronegativities. For hydrogen, that's 2.1. For fluorine, that is 4. The difference between these two values is 1.9. That is greater than 0.5. Therefore, hydrofluoric acid is polar. But that is also a molecule. So we have London force. In addition, we have the force that is present only in the non-covalent intermolecular force present only in polar molecules, which is the dipole-dipole force. Okay, now let's consider water. The shape of water is like this one. So you have oxygen, then we have hydrogen below, two hydrogen atoms below. Okay, now in a previous slide, we determined that the hydrogen-oxygen bond is polar. Okay, and they are not positioned directly opposite each other. Therefore, they will not cancel out. Okay, so therefore, water is a polar molecule. Okay, so as in the case of hydrofluoric acid, so we have London force. In addition to that, we have dipole-dipole, and we also have here a hydrogen atom. Well, actually, two hydrogen atoms bonded to an oxygen. And this oxygen, by the way, has two lone electron pairs. So, hydrogen bond is possible. Okay, so again, in addition to the first two, we have hydrogen bond. Hold on, let me locate the pen. Okay, now let's consider methanol. Methanol, okay, has this structure. So we have CH3 bonded to an oxygen, okay, which is bonded to a hydrogen. In this case, the oxygen also has two lone electron pairs. Okay, so again, the hydrogen-oxygen bond is polar, and there's nothing to cancel out this polar bond. Okay, so therefore methanol is also polar. Okay, for the non-covalent intermolecular forces, we also have London, we have dipole-dipole, and since we have a hydrogen atom bonded to an oxygen atom, okay, we have lone electron pairs in oxygen. Yes, okay, so in methanol, hydrogen bonding is also possible. So we have hydrogen bond. And yes, again, hydrogen bond is the strongest among the three non-covalent intermolecular forces. Okay, so for the question of which substance has the highest boiling point, it looks like we have to compare water and methanol. Okay, because they both have hydrogen bonds. Okay, so whichever substance has more hydrogen bonds, okay, so that substance should have higher boiling points. Okay, so let's count the number of hydrogen bonds in water. So this hydrogen, okay, can bond with uh, one of the lone electron pairs in the oxygen atom of another water molecule. Okay, the same is true of this other hydrogen atom. So that's one. So we have one. So far we have one, two hydrogen bonds. Okay, next, each of these lone electron pairs, okay, will be attracted to a hydrogen atom from another water molecule, and the same is true of this other lone electron pair. So in water we have one, two, three, and four hydrogen bonds. Now let's consider methanol. So this hydrogen atom, sorry, which is bonded to an oxygen atom, okay, can bond with um, with a lone electron pair in an oxygen in the oxygen of another molecule. So that's one hydrogen bond. Each of these lone electron pairs, okay, can in turn bond with a hydrogen atom from another molecule of another molecule. Hold on, let me locate the pen. Okay, there it is. Okay, so hydrogen, okay, bond with hydrogen. So again, we have one hydrogen bond, then two and three. Okay, since water has four and methanol has only three hydrogen bonds, then hydrogen bonding is stronger in water. Therefore, water has the highest boiling point. Okay, water has the highest boiling point. And that's it. Thank you for watching.